Okay, first question is proof by contradiction, and we always start by assuming the opposite. So we're going to assume if P and Q are positive integers, then P over Q plus Q over P. Now what's the opposite of being greater than or equal to 2? It's less than 2. Okay, now we're going to do the algebra. Let's make this a single fraction. This whole thing here, let's add these two fractions together. So times this one top and bottom by P, it's going to give me P squared over PQ. And times this one top and bottom by Q, it's going to give us Q squared over PQ. And that is less than 2. Okay, so then we can write that as P squared plus Q squared all over that common denominator of PQ. Okay, so the next natural thing would be to multiply both sides by PQ to clear the denominator. So we get P squared plus Q squared is less than 2PQ. And then a lot of times when we have this a proof question which has like less than or greater than or something, then it's a good idea to get it all onto one side so that we are looking at less than or greater than 0. So here we're going to have P squared, I'm going to minus the 2PQ and then plus Q squared, and that needs to be less than 0. Now I put it in the middle because I've got an idea that we're going to factorize this in order to create a square bracket. And yes, this does factorize. This factorizes to P minus Q times P minus Q. Yes, it does. Let's double check. P times P is P squared. Minus Q times minus Q is Q squared. And then we've got the P times Q is minus PQ, and the Q times P is also minus PQ. So we've got those two minus PQs. Great, so we can write this as a square. And as we know, squares are always greater than 0. So we can say that as P minus Q is greater than 0, we have a contradiction. We have contradiction. Hence P over Q plus Q over P is greater than or equal to 2. Or we can say the original statement is true, but I always like to write out the actual bit which is true, and that is job done. Okay, log modelling. Now if I do a question like this, I always take the formula and then take the log of both sides. So we'll do log of y is equal to log of akx, and then we'll split that log on the right up, that should be log e, there you go, which is log a plus log k to the x. We'll then bring down the power, because when you're doing a log rule like this, you can bring the power down to the front. And then what I'll do is I'll write it in such a way that it looks like y equals mx plus c. So we'll do log k will be the gradient m, times it by x, and then plus a constant, which will be log a, the y-intercept. Okay, now, like I said, this can now be compared with capital Y is equal to gradient x plus c. Okay, so what that means is that if we plot log y as one variable, like we have here, because we're told that log y is going to be capital Y, and then we plot that against the other variable, which is just x. So we plot against x, then we should get a straight line because it's in the form of y equals mx plus c. So what does that mean? It means that log k is going to be the gradient. Okay, so let's find the gradient. So the gradient is going to equal the change in the y, which is 3 minus 0, over the change in the x, which is 0 minus 3 over 2. So that is the same as 3 over 3 over 2, which is equal to 6 over 3, which is just 2. And because we've said that m is equal to log k, we can say that log k is equal to 2. So therefore k is equal to 10 to the power of 2 by reversing this log equation into an indice equation, because we are using base 10 here. So this is log base 10. So if we take it to the 10 to the so if log base 10 of k is equal to 2, then k is equal to 10 to the power of 2. Okay, great. So that means that k is equal to 100. And then we also know that here log a is equal to c, and c is the y-intercept of a straight line, and the y-intercept here is 3. So we can say that log a is equal to 3, and once again this is to the power 10. So therefore a is equal to 10 to the power of 3, which is equal to 1000. Perfect. Okay, log equation, absolute classic this one. So what we're going to do is we're going to use our log rules. We're going to take this 2 and we're going to make it a power of x, because what we want to do really is simplify this left side and combine all of those logs together. So this is log of x squared plus log of x minus 1, and then log of 5x plus 4. Okay, so now we can combine them all. The ones that are added together, those are going to be on the numerator of our fraction. So we'll have this on the top, and then this one is subtracted, so that one is going to go on the bottom, because log of a plus b means we times them together to make log of ab, and then log of a minus b means we divide them to get log of a divided by b. So because we're minusing this one, that's the one that goes on the bottom, and the other two are going to go on the top. And that's equal to 1. And now if we have, in this situation, log base 2 of a is equal to 1, then this is the same as writing that as an indice rule of a is equal to 2 to the 1. So therefore we can say this thing inside the bracket is going to give us equal to 2 to the 1, which is just 2. Okay, then we can multiply up the denominator to get 10x plus 8 by timesing that denominator by 2. And then we can expand the brackets like so, set that equal to 10x plus 8. Bring it all over to one side, and we've got a cubic to solve. Now it's probably unlikely that EDEXCEL gives you a cubic to solve without any like prompting or like a bit of help about how to solve it. But this is a MADAS question, and you know, he's just like, get on with it, solve it. So we'll do it by inspection. We'll try 1 first. Does 1 work? That would be 1 minus 1 is 0. Then minus 10 minus 8. So that doesn't work. But let's try if we sub in f of minus 1. Then we get minus 1 cubed minus 1 squared minus 10 times minus 1 minus 8, which is the same as minus 1 plus 10 minus 8, which equals 0. So that's good, that works. And that means that, by the factor theorem, x plus 1 is a factor, which means we can divide our polynomial by x plus 1. Okay, let's just give myself a tiny little bit more space by moving down. Okay, and so how many x's go into x cubed? That would be x squared times the x squared down. We'll get x cubed plus x squared, and then we subtract. This will give us minus 2x squared, and we'll bring down the minus 10 as well. Minus 10x, sorry, and the minus 8, why not? And then how many x's can we fit into minus 2x squared? That would be minus 2x. Then multiply that by what we're dividing by, and we get this. Then we're going to subtract. This is going to give us minus 8x minus 8. And then how many x's can we fit into this? Minus 8. Multiply the minus 8 by the x plus 1. Does it work? Does it give us 0? Yes, it does. That's perfect. And that means our new, not a new equation, but rewritten equation is going to be the thing we're dividing by, new quadratic is equal to 0. And that's what we're trying to solve. Okay, factorize this quadratic. No problem, that is x minus 4x plus 2. So therefore we're going to get three answers. We're going to get minus 1, we're going to get 4, and we're going to get minus 2. Now, with any log equation, you've got to go back and check to see if, when subbing in the solution, it doesn't give us a log of a negative number. And this one is seriously not looking good. X minus 1. So if for that to be greater than 0, which it needs to be, we could say that x minus 1 needs to be greater than 0, because we can't input a negative number into a log. So that means that x needs to be greater than 1. So bye-bye, bye-bye, and hello to x equals 4. Final answer. Okay, functions. Everyone hates finding the range, but we're going to have to do it straight away. And it's a fraction. Okay, so that's important, which means it'll probably have a limit to it. So first off, let's just start with the domain being x is greater than 0. So let's just start by subbing in 0. Now I know what you're going to say, but it can't be 0. Yes, that's true, but it's going to give us the lowest value that it, very close that it could be. Anyway, if we sub in x equals 0, we get that g of 0 is equal to 0 over 3, which is equal to 0. Okay, now if we sub in, okay, so that's basically going to give us a lower bound. Like it won't equal 0, I know, but it will be pretty much as close to 0 as it can get. Now let's look at the limit. So let's just imagine what would happen if you sub in a huge number. Let's just call that big number m. Then we're going to get 6 lots of a huge number over 2 lots of a huge number plus 3. Now, because that number is so big, the plus 3 really doesn't matter. Doesn't matter at all. So we're left with just 6m over 2m, which is just 3. So what that means is that when you get a huge number, this function is going to tend towards 3. It won't actually hit 3 because there is this tiny plus 3 on the bottom, but it's going to tend towards it. So that means that we are stuck in between 0 and 3. So our answer is going to be that it is between 0 and 3, where we can't equal either of them. Now once again, it's important to write it as g of x. If you put x there, then you're not going to get the correct answer, I'm afraid. So you have to put g of x there. Okay. Next one, it says find the inverse of g. So what we do is we set the function g equal to y, like so. And then the inverse function is the reflection of the function in the line y equals x. So what we do is we do that line reflection for y equals x by just swapping the y for the x. So this gives us x equals 6y over 2y plus 3, like so. We then need to rearrange to make y the subject again. So I take the denominator and I multiply it to the other side. So we get x lots of 2y plus 3 is equal to 6y, which gives me 2xy plus 3x is equal to 6y. Now we want to make y the subject, so we need to bring all of the y terms to one side. And I'll do that, in fact, just by moving the 2xy to this side. It becomes minus 2xy. We then need to factorise. So we factorise out y to get 6 minus 2x. And then finally we can divide through by that 6 minus 2x to get y. And then we must write it like this. G to the minus 1 of x is equal to 3x over 6 minus 2x. Now it says to state the domain, which is important when you are creating an inverse function. You must state the domain, even if the question doesn't ask for it. I have seen questions where you still need to state the domain. And the domain of the inverse is the same as the range of the original. But when we write domain, we must write x, not g of x. So it's 0, x, 3. And that will be the domain of the inverse because it is the same as the range of the original. Okay, perfect. And now it says find g of x, giving your answer as a single fraction in its simplest form. Okay, so there's g of x at the top. Let's just remember that it's 6x plus over 2x plus 3. And we're just going to replace every x with g of x itself. Okay. So part C, g of x is going to equal, so it was 6x over 2x plus 3. But instead of putting x in, we're going to put g of x in itself, which was 6x over 2x plus 3, 6x over 2x plus 3. Okay, right, not ideal this, but what we're going to do is we're going to multiply top and bottom by the denominator, which is being a little bit annoying. So let's multiply the top line by 2x plus 3 and the bottom line by 2x plus 3. Okay, so multiplying this by 2x plus 3 just cancels the divide by 2x plus 3, so you're just left with 6 times 6x, which is 36x. Doing the same here, we'll just cancel that denominator, which will leave you with 2 times 6x, which is 12x. But you also have to times the 2x plus 3 to the 3 as well. And in doing so, we get 3 times 2x plus 3, which is 6x plus 9. We'll tidy that up to get 36x over 18x plus 9. And then we'll tidy it up further by dividing through completely by 9 to get this. And that will be our final answer. Love a functions question. Okay, modulus functions. So we have f and we have g. It says find the inverse function of f and state its domain. Okay, so a little bit more functions squeezed in here, which is good because functions is such an important topic and I suspect it's going to come up. Find the inverse and state its domain. So we're going to do the same thing. We're going to set y equal to e to the 2x minus 5. We're then going to do the xy swap, like so. And then we're going to make y the subject again. So add 5 to both sides. Take the natural logarithm of both sides. And then divide by 2 or times by half, same thing. To get this, so then we write f dash of x is equal to 1/2 ln of x plus 5, like so. Okay, perfect. Now we're asked for the domain of the inverse function, so it might be easier to look at the range of the original. Now e to the 2x or e to the x of any sort is always greater than 0. So therefore, if we've got e to the 2x minus 5, that's going to be always greater than minus 5. So the range of f is greater than minus 5, which means the inverse function is going to be that x is greater than minus 5. That's the domain of the inverse. Okay, because the range of the original is that f of x, sorry, is greater than -5. Okay, voila. Next part, it says find f of g of 3, giving your answer in the simplest form. Okay, so that's part B. So first off, we find g of 3, which means we put 3 into g, which gives us ln of 3 times 3 minus 1, which is equal to ln of 9 minus 1, so ln 8. And then we put that into f. So f of g of 3 is the same as f of ln 8. And putting ln 8 into f is going to give us e to the 2 lots of ln 8 minus 5, which is the same as e. Now if we can move this 2 up to the power, then it will put the e and the ln next to each other, which will cancel out. So it'll be e to the ln of 8 squared minus 5, which is e to the ln of 64 and minus 5, and then that e and the ln will cancel out, so we just get 64 minus 5, which is equal to 59. Perfect. Okay, let me box that up, and then we'll move on to the next part of the question. Perfect. Okay, so we have to sketch the graph with that equation. Okay, so I'm going to draw myself an axis, like so. And then I'm just going to imagine there was no modulus sign there. So this graph would have a gradient of 4 and a y-intercept of minus a. So let's say that's minus a, and then a gradient, a positive gradient of 4, it would come up something like this. So this will be minus a, where it cuts there. It does say the coordinates, so sometimes I get a bit worried that just by writing the actual y value there, you may not get the mark. So if you write it as a coordinate, I think you'll be alright, but anyway, I better be careful. And then this point here, that's when the y is 0, so that's when 4x minus a is equal to 0, so therefore x is equal to a over 4. So that would be a over 4, and then this will be 0 right there. Okay, great. Now what we do is we reflect it in the x-axis. So the line comes down like this, hits there, and then comes up over here, like so. So in fact, this coordinate here is going to get reflected over here. So it's actually the one that we want is going to be 0, positive a. Okay, great. So we can get rid of this bit underneath the axes. We don't need this anymore. And there we go. That is it. That is sketched and done. Perfect. Okay, so next it says, given that this modulus, which we've just graphed, is equal to 9a. So if I was to draw y is equal to 9a, then it would look something like this. But I mean, that's not to scale, of course, because if this is 9a and that's 1a, then obviously it's not to scale, but again, it's just a sketch, so that will do the job. And that would be 9a where it hits the y-axis. Okay, so that just gives us a help to visualize how many solutions we should expect. And you can see that it's going to cut twice, so we should expect 2 solutions. Okay, so let's solve that, and then we can move on and answer the next part of the question. So where do these 2 things meet? Well, first off, if we take the positive part, then we'll get 4x minus a is equal to 9a, which means 4x is equal to 10a, which means x is equal to 2.5a. Okay, perfect. So over there, that must be 2.5a where they hit, where x is 2.5a. And then this one, this side here, we need to take the negative of the modulus. So we could write that as either minus 4x plus a, or you could just do a minus 4x. Let's just do that. So a minus 4x, and that's equal to 9a. So just making this completely negative. So that tells me that 4x is equal to minus 8a. I think. Move that over there. Yeah, that does the job. So x is equal to minus 2a. Okay, great. So that is definitely going to be helpful. Those are the two x values that solve this equation, which we've been told is true. So now it says find the possible values of this. Okay, well we can do that using these two x values. Okay, so let's just grab a bit more space. And then let's take the modulus of x minus 6a plus 3 the modulus of x. And then we can say when x is equal to 2.5a, what do we get? Well, we get the modulus of 2.5a minus 6a plus 3 lots of the modulus of 2.5a. So this is 2.5 minus 6, which makes a total of minus 3.5. And then the modulus here is not doing anything because that's positive anyway, so times it by 3 is 7.5a. Now the modulus turns this positive, like so, and then we add those together, we get a total of 11a. Okay, so that is one solution. Now the other solution is going to come by substituting in x is equal to minus 2a. So using this one here. Okay, so when x is equal to minus 2a, we will get the modulus of x, which is minus 2a, minus 6a, plus 3 lots of the modulus of a, which is the modulus of x, sorry, which is minus 2a. Okay, so this is modulus of minus 8a plus okay, so what is this? So the modulus of minus 2a is positive 2a, so we always take the positive, times by 3, so that's just 6a. So this is 8a plus 6a, which is overall 14a. So those are our two answers for this question. Lovely. Okay, binomial expansion, absolute classic. Find the series expansion of f of x in ascending powers up to and including the x to the cube term. Oh, wowzer. Okay, so let's rewrite this in a way which we can then expand it, which would be to write it as a negative power like this. Okay, then we need this term in here to be 1, so we've got to take out a factor of 3. And we take out a factor of 3. And when we do that, we must take out the power with it. And that will allow us to divide inside the bracket by 3, which gives us this. Okay, great. Now this is 1 over 9, so times by 27 is just going to be 3. Okay, great. Now to the formula. Which is in your formula booklet, and what I like to do is I like to say that the n is going to be the power and the x is in fact going to be whatever this term is here, which is minus 5 over 3x. Okay, so now we can say that f of x is approximately equal to, because we're going to not do all the terms, 3 lots of, because the 3, we're just going to get that out of the way. But don't forget about it, because how many times have I done this and I forget about that constant outside. Anyway, it's 1 plus nx is the start of the formula. And then it's plus n minus 1 x squared over 2 factorial plus n minus 1 n minus 2 x cubed over 3 factorial. And that's all we need to go up to. Okay, so now time to simplify. 1 this will give us plus 10 over 3x. I definitely don't want to do this in my head because I will make a mistake and that is not time efficient. Minus 2 times minus 3 times, in brackets, minus 5 over 3 squared, and then we need to divide that all by 2 factorial to get plus 25 over 3x squared. Okay, and then next it's minus 2. Let's just do a little bit in our heads. Come on, we can do that, can't we? Minus 2 times minus 3 is 6, which actually cancels with the 3 factorial. So we've got minus 4. So we've just got minus 4. Oops. And we're going to times that by minus 5 over 3 to the power of 3. Okay, great. So that's plus 500 over 27x cubed. Close bracket, and then we've got to times that by 3. Don't forget to do that. So timesing through by 3 is going to give us this, and that will give us 500 over 9x cubed. Okay, fantastic. That is correct. Love that. Love that a lot. Okay, right, on to part B, and it says that we need to use our answer to part A, okay, the one we've already worked out, to then work out the expansion of this one here. So what's the difference? Well, here we've got a minus, but this new one we've got a plus. Okay, so how is that going to change? Well, if we write over here, part B, n is still going to be minus 2 because the power is still the same, but the x is no longer going to be minus 5 over 3x. It's going to be 5 over 3x, positive. Okay, so that means that this here is going to change to a positive. So, in fact, the first term is going to stay completely unchanged because the first term is just 1 times by 3, so that's going to become unchanged. Now this one, that minus is going to turn into a plus, which means overall we're only going to have one minus in this term, so therefore rather than two minuses making a plus, we're going to have just one minus, so it's going to be minus 10x. Now over here, this minus is going to change to a plus, but that's not going to affect that term at all, because that minus is going to get squared, so it's going to be a plus anyway. So if we swap it for a plus, it's still going to be a plus. So that's going to be plus 25x squared. Now this minus, so because that's cubed, that minus did actually have an effect. But because we're now going to turn that to a plus, overall this will be a plus rather than a minus, which is going to change the sign. So rather than having plus 500 over 9, we're going to have minus 500 over 9. Because when that's a plus, we're just going to end up having these three negatives, which is going to make the whole thing negative. Okay, so that is part... that's part B. Now what's going to happen with part C? So what's the change here? So now we've just got minus x as opposed to minus 5x. Okay, so the x value is essentially 5 times smaller. So we're still going to have n equals minus 2, but the x, rather than being minus 5 over 3x, it's just going to be minus 1 over 3x. It's going to be 5 times smaller than the original that we did. So how is that going to affect the expansion? Well, let's have a look at where does the 5 come into play. Well, it comes into play here, here, and here. So that means the first term, the 1, is again going to be unaffected. Times it by 3, it's going to be 3. The second term is going to be, that 5 is going to turn to a 1, so it's going to be 5 times smaller. So rather than 10, it's going to be 2x. And here, this 5 is going to turn into a 1, but that 5 is squared to make 25. So having a 1 there is actually going to mean it's going to be 25 times smaller. So that term needs to be divided by 25. And the last one, we're going to have this 5 here going to be cubed, but now we're turning it into a 1, so it's going to be 125 times smaller. So this needs to be divided by 125, which gives you 4 over 9 x cubed. And there are our answers to part B and part C in what is a lovely binomial expansion question. Perfect. Okay, geometric sequences, and we've got wheat is to be grown on a farm. A model predicts that the mass of the wheat harvest on the farm will increase by 1.5% per year. Okay, so that means that R is equal to 1.015 because that's adding on 1.5% to 100% and then turning it into a decimal, so that will be the common ratio. Year 1, it's 6,000 tons, so we say that A is 6,000. Then it says, show that according to the model, the mass of the wheat harvest on the farm during year 4 will be approximately this. Okay, so year 4 means we're looking for the fourth term. So in a geometric sequence, the fourth term is equal to A R to the 3, because it's always A times R to the n minus 1. So this is 6,000 multiplied by 1.015 to the power of 3. And we can do that on our calculator, no problem. So 6,000 multiplied by 1.015 to the power of 3. And we get that that is 6274. And that will be tons. And that will be the correct answer that we are looking for. Okay, perfect. Right, part B. It says, during year N, according to the model, there is predicted to be more than 8,000 tons, so greater than 8,000 of wheat harvested on the farm. Find the possible value of N. Okay, so A capital N is equal to AR to the power of n minus 1. And we want that to be greater than 8,000. Okay, fine, let's solve that equation then. So A was 6,000, R n minus 1 greater than 8,000. Okay, so let's then divide by 6,000 on both sides, and 8,000 divided by 6,000 is 4 over 3. Let's take log of both sides, like so. Let's bring that power down, so n minus 1 log of r, and of course r, should have put this in earlier, is 1.015. We know what r is. Okay, so then we can just divide these two logs. Now be careful, is that a negative? Well, no, it's not, so it means we don't need to swap the sign over. But sometimes if we have log of a number which is less than 1, then it will give us a negative value. When we divide by a negative, we have to swap the sign over. But in this case, we do not, because, yeah, it's not negative. Okay, so this over this plus 1. Okay, so we'll do that on our calculator. That was pretty rapid actually. I'm pretty chuffed with that. So n is greater than 20.32, which means that n must equal 21 because it is needs to be greater than 20.3, so it must be 21. Perfect. Okay, next part it says assuming oh actually I need a bit more information from above. Whoa, not that far. Okay, so it says it costs £5 per tonne to harvest wheat. Okay, so assuming the model find the total amount that it would cost to harvest the wheat from year 1 to year 10 inclusive, give your answer to the nearest £1,000. Okay, so that means that we need to use a summation formula. So we're summing the first 10 terms inclusive, and that is equal to a 1 minus r to the power 10 all over 1 minus r. That's your classic summation formula. So that's going to equal 6,000 1 minus 1.015 to the power 10 all over 1 minus 1.015. Okay, so again that can just go into our calculators. Okay, and that gives us 64216.3, and that is tons of wheat. So the cost is equal to the amount of tons multiplied by the price, which is £5 per tonne. So multiply that by 5, and we get in pounds 321. It says the nearest 1,000, so just 321,000, and that is perfect. Lovely. Okay, we've got recursive and summation sequences. So we've got a sequence is defined, u1 is equal to 1, and then the next term is k minus 8 over the previous term, where k is a constant. Write down the expressions for u2 and u3. Okay, so u2, other than being a fantastic rock band, will equal k minus 8 over the previous term, which is 1. So that's just equal to simply k minus 8. Okay, great. u3 is equal to k minus 8 over the previous term, which is k minus 8. Okay, great. It would probably be an idea to simplify that, but they don't actually ask us to simplify it, so I'm just going to leave it like that. You're just going to run the risk of making a mistake if you end up simplifying it. I think you probably get the mark if you've written it out correctly and then try to simplify and get it wrong, but who knows. Part B. Given that u3 is equal to 6, so that means that 6 is equal to this k minus 8 over k minus 8. Find the possible values of k. Okay, so let's multiply the whole equation through by k minus 8. So that will give me on the left side 6 lots of k minus 8 is equal to k times by k minus 8, and then this final term, if I times it by k minus 8, it gets rid of the denominator, which just leaves me with 8, and there's a minus there as well, so minus 8. Perfect. So now let's expand the brackets on this side as well. Let's bring it all over to one side. We'll bring it all over to the right side because that's the side with the k squared in order to keep that positive. So minus 6k gives me minus 14k. Add 48 gives me plus 40. Okay, does that factorize? I think it does. So I think that is k minus 4, k minus 10. Which gives us k is equal to 4 and k is equal to 10. And then always worth, just when you get your answers, just scroll up and see, is there anything here which is going to maybe stop one of these answers being correct? In this instance it says k is a constant, so that's fine. And here it says possible values of k, so that values is giving me confident that there's going to be more than one answer. So I'm pretty confident that I've got it right, and then we can move on. So that just little 15-second check can be so important and could save you a decent number of marks. Okay, small angle approximation. When x is measured in radians, then there are certain things that we need to know. And that is that sine theta is approximately theta. Cos theta is the tricky one. That one's approximately 1 minus theta squared over 2. And tan theta, for that matter, is also approximately theta. So what do we have here? We have cos x minus 1 over x sine x. So cos 7x minus 1 over x sine x. So cos 7x is going to be this, let's just write this out. Cos 7x is going to be approximately 1 minus 7x squared over 2. Just using this relationship here, but we're swapping the theta for 7x. Okay, so now let's put this together by writing that cos 7x minus 1 over x sine x is going to be approximately equal to, well, we know cos 7x is 1 minus, now what is this? So 7x all squared is 49x squared over 2. So that's the that's the cos 7x sorted. Then there's the minus 1 here, so minus 1, and then that's all over x, and then sine x is also x, because sine theta is approximately theta, so sine x is approximately x. Okay, great. So what is going to cancel here? We've got a 1 and a minus 1. So on the top we're just left with minus 49x squared over 2, and then that we need to divide by x times x, which is x squared. Okay, great. So what's going to cancel here? So we've got x squared on top and then x squared on bottom, so they will cancel. So therefore we're going to have, this is going to be just minus, don't forget that, 49 over 2, and that's it. That's job done. Beautiful. Okay, trig modelling. Love these questions. Easiest 3 marks you get on the paper, as long as you know this little hack. Now we are converting into sine. So therefore, I'm going to write the sine bit first, and then the cos bit second. This means that the first coefficient there, I'm going to call A, and then the second coefficient is going to be my B. And once you've done that, that is basically the hard work done. So just make sure that whatever trig function you're converting into, that is going to be your A, and then the other one will be your B. So then what you could do is you could say that R is equal to the square root of A squared plus B squared. So in this case it's the square root of 2 squared plus 4 squared, which is going to equal the square root of 16 plus 4 is 20, which is going to be 2 root 5. And then alpha is always equal to tan to the minus 1 of B over A, which is going to equal tan to the minus 1 of 4 over 2, which we could do on our calculator. So we can go to in radian mode. 4 over 2. Okay, so alpha is equal to 1.107, and that's it. So there are our answers. 3 marks. You can expand out the harmonic form, and I know some people do that, but I like this little shortcut because it saves time. Okay. Next, it says in a town in Norway, a student records the number of hours of daylight every day for a year. He models the hours of daylight h by the continuous function given by this formula. Okay, great. T is the number of days. Always, always, always highlight the units. Very important. Okay, and h is the number of hours. Okay, so using part A, find the maximum and minimum number of hours of daylight given by this formula. Okay, so let's rewrite this function here using the harmonic form. So important to note that the one that we did here, it just had x, but now in this one we have this different input. So basically x is now going to become 2 pi t over 365. Okay, so what we can do is we can say that let's just write out the harmonic form bit first actually. So that was that 2 sine x minus 4 cos x was equivalent to 2 root 5 sine x minus alpha, which was like this. Okay, now let's convert h using this information. So h is equal to 12, so that's just going to stay the same, that's constant. But here you can see that the coefficients of the sine and cos are 2 times bigger. So this is going to plus 2 times the harmonic form which we worked out, which was 2 root 5 sine x, but x is swapped out for 2 pi t over 365 minus 1.107. Okay, great. So that is our new formula for h. And we're going to say this is 4 root 5, because just times the 2 by the 2, just to tidy it up. Like so. Okay, so now what we're trying to find is the maximum and minimum. So the max will happen when this sine function here is maxed out. And we know that the maximum sine can be is positive 1. So when this is positive 1, this sine function, times that by 4 root 5 is just 4 root 5. So that is the max value. It says give your answer to 3 significant figures, because we are modelling, so it's important to not necessarily give it an exact form. Okay, so that is equal to 20.94, and that is hours of sunlight. Okay, next it's also asking for the minimum. So h minimum is going to be 12. And then when's the minimum going to happen? When the sine function is minus 1. Times minus 1 by the 4 root 5 gives us minus 4 root 5. So now what we need to do is just change that to a minus. So that is equal to 3.06 hours. And I've just realised it says give it to 3 significant figures, so I need to knock that 4 off. Nice. And again, not read the question, rushing here, I've just realised that this asked me to give it to 3 significant figures as well. Okay, right, don't scream at me in the comments. I'm sorry, I didn't read the question. And that should hopefully remind you that it's so important to read the question. So that's like extra bit of knowledge there that you've gained by my mistake. Anyway, if that's the 3 significant figures, then this should just be 1.11, which means you should be 1.11. And luckily it has had no effect on the question so far. So just change it. Just change this, and that's just going to be like it never happened, guys. Like it never happened. Okay, part C. Use the formula to find the values of t when h is equal to 17. Give your answer to the nearest integer. Again, one of the most important words in the whole of your paper is this one, value or values. So it gives you an indication of how many answers you should be expecting. Okay, so where's that formula for h? Right, here it is here, and we want h to be 17. So we say 17 is equal to 12 plus 4 root 5 sine of 2 pi t over 365 minus 1.11. Okay, let's rearrange this so we can minus the 12 to make 5, and then we can divide by this 4 root 5, and that will give us just the sine function, which will look like so. Okay, now before we are going to do inverse sine, I want to just check what the range is for t. Go all the way back to the top, and it tells me that t is between 0 and 365. Okay, so I'll come back down here, and what I'll do is I'll just write that on the side. I'll say that it's between 0 and 365. And then we're going to transform this range into, so t is going to turn into 2 pi t over 365 minus 1.11. Okay, so when t is 0, this is just going to be minus 1.11. Here is 2 pi t over 365 minus 1.11. And then when t is 365, well, we do 365 times by 2 pi divided by 365 and then minus 1.11. And that's going to give us 5.17. Okay, so we've just converted that range. So now we're just looking for values when we do inverse sine that are going to be in this range here. So we'll do inverse sine of both sides, like so, and this will give us 2 pi t over 365 minus 1.1. So what is that inverse sine? So inverse sine of 5 over 4 root 5 will give us, okay, brilliant. So that means that 2 pi t over 365 minus 1.11 is equal to 0.593. Now wait, soon as you have done inverse sine or inverse cos or inverse tan on your calculator, I want you to find the second value straight away. Okay? Now the second value for sine is pi minus the original. Okay, great. So that is 2.55. Now these are the two important values, and what we're going to do is we're going to add 2 pi to them, like so, and also we're going to minus 2 pi to them, and we're going to see if there are any that are in the range. Okay, so let's take this one because it's in the calculator now, and let's minus 2 pi. That is outside of the range. Okay, it's outside of this range here. It's outside of that range. So therefore that is no good. And in fact, if we were to take 0.593 and minus 2 pi, that will also be outside of the range. So going backwards is actually no help here. What about going forwards? Okay, let's get that number back. There it is. And if we add 2 pi to that, that's outside of the range because the range is 5 on the higher side. It's 5.17, so that's too much. Okay, let's take this guy and let's add on 2 pi to that. That is also outside of the range, so that is no good. So in fact, it's just these two times which are going to be the ones that fall inside the range. Now you may say, well, could you not just got on with it rather than doing all this faffing around? Well, maybe, but I like to make sure that I've got all the solutions because I don't want to lose any marks. Okay, now what we need to do is we need to just solve for t now. Okay, so we're going to take that 0.593 and we are going to run it through the formula by adding 1.1 to both sides. Then we're going to times it by 365. And then we're going to divide it by 2 pi. Okay, great. So that gives us 8.9. Okay, which is approximately 99 days. And then we're going to do the same, but we're going to take that second solution. So by doing it like this on my calculator, it just allows me to just enter the second solution like so, and then just press equals. Okay, so that also gives me 212.6, which is approximately 213 days. And there we have it, our final answers in what was quite a beastly question. Perfect. Okay, first principles. Absolute classic. This is to differentiate sine into cos. Okay, so we get given these things here. So what is the formula for first principles? Well, it's f dash of x is equal to the limit as h tends to 0 of f of x plus h minus f of x all over h. Now that is given in your formula book, so you don't need to worry about memorizing it. Okay, so how do we work this? Well, first off, the function we're trying to differentiate is sine. So we say f of x is equal to sine x. We're then going to need to work out f of x plus h, which will be sine of x plus h. Now, using the compound angle formula, which again is given in your formula book, this will be sine x cos h plus sine h cos x, like so. Okay, great. So that's going to be helpful. That's just on the side. Let's now follow the process of actually using the first principles. Okay, so it's the limit as h tends to 0 of f of x plus h, which is this over here. So that's sine x cos x plus sine h cos x. Okay, let's just grab a bit more space because I don't want to run out of space here. Let's just scooch you over a little bit. Okay, and then what we need to do is we need to subtract f of x. So that's minus, and f of x is just sine x, like so, and then that is all over h. Now the idea is we're going to want to factorize this expression to get both of these two factors somehow, because we know what the limits of those are. Okay, so let's just do a little bit of factorizing here. So what we can say is we can take out a sine x. So how many sine x's do we have? Well, we've got cos h of 1 here. This one doesn't have a sine x in, but this is a sine x, and it's minus one of those, so minus one of those. And then we can divide that all by h, because the whole numerator is divided by h, so we can just put the h here, and this would be true. Now what have we missed out? We've missed out this term here, and we can take out a cos x of that, which just leaves sine x here, sine h there, and we can write that over h like that. So just check to make sure that this expands out perfectly to give you the line above, which it does, so I'm pretty happy with that. Okay, and then we could say that as h tends to 0, we know that cos minus 1, cos h minus 1 over h tends to 0, as we're told up here, and sine h over h tends to 1. Okay, so then we can say that f dash of x is equal to, now we're going to have sine x here, but this cos h minus 1 over h is going to tend to 0, so that's going to be 0, and then plus cos x here, and this sine h over h is going to tend to 1, so that's going to be times by 1. So this is just going to give us f dash of x is equal to cos x, and that's exactly what we're looking for. So that is all good. Perfect. Okay, next question, and we have a graph here, and it says that we've got f of x is equal to this. The curve has a minimum turning point at A. Okay, so this looks like we're going to be using the product rule here. It says use calculus to find the exact value of A. So if we're trying to find a turning point, we need to take the function and we need to differentiate it, set it equal to 0. So we'll start by taking the derivative. Okay, so we're going to need to use the product rule. So what I'll do is I'll write u is equal to 2x minus 5 and v is equal to e to the x. We'll differentiate this with respect to x to get 2, and we'll differentiate this with respect to x to get e to the x. Now, the product rule means that we need to multiply this by this, and then we need to add it to the multiplying of this by this. Okay, so we're going to do 2x minus 5 times e to the x plus 2 times e to the x. Lovely, and we want that to equal 0 because we're trying to find a turning point, and that's where the derivative equals 0. So to solve an equation equal to 0, it's a really good idea to factorize. So I can take out an e to x of both expressions, which leaves 2x minus 5 for the first expression, and then plus 2 for the next one. And then let's simplify this bracket here. We've got 2x minus 5 and then plus 2, so that's just 2x minus 3. Okay, so when is this going to be 0? Well, e to the x can never be 0. So e to the x does not equal 0. So therefore we're going to need 2x minus 3 to equal 0, which means x is going to equal 3 over 2. Okay, so we're going to scroll up and we are going to say that it says use calculus to find the exact coordinates of A. So calculate is going to be pretty useless here. Let's sub in to get the exact value. Okay, so we can say that f of 3 over 2 is equal to 2 lots of 3 over 2 minus 5 times by e to the 3 over 2. This will be 3 minus 5 is minus 2, and then e to the 3 over 2, leave it like that as an exact value, which means that A has x coordinate 3 over 2 and y coordinate minus 2e to the 3 over 2. Perfect. Okay, so that is the A coordinate done. Right, moving on to part B, it says that the equation f of x is equal to k, where k is a constant, has exactly 2 roots. State the range of possible values of k. Okay, so f of x is already drawn for us. Of course, it is this curve right here. And k, so y equals k, will be a horizontal line, like so. And we need to find where they're equal, which means where they cross. And we're told that it has 2 roots, so therefore they're going to cross twice. Okay, so we need to find where they're going to cross twice, or what value of k will make them cross twice. So let me just pick this up, and then let's imagine moving it, so changing the k value. And you can see here that they're actually still only crossing once. But when we get to here, this is where they're going to start crossing twice. I know it's hard to see, but this down the bottom is going to tend to 0. So therefore, right here at some point all the way down the line that way. Which way? Yeah, that way, all the way over there. Eventually it will hit, and then it's going to keep hitting until it gets to here. That's where it's going to stop. Okay, so if I just take this and this, so those in between there is where it's going to hit twice. And this is y is equal to 0, and this is y is equal to the y coordinate of the turning point, which is minus 2e to the 3 over 2. So therefore, we can say that k needs to be in between these 2 points. So for part B, we can say that k is in between 0 and, whoops, it's actually, let's do the smaller one first. So minus 2e to the 3 over 2 is less than k, which is less than 0. So it's in between those 2 points. Okay, perfect. Right, so now it says sketch the curve with equation f of x, the modulus of such, indicate clearly your sketch, the coordinates where it crosses or meets the axis. Okay. So what I'll do is I'll do it on this diagram because I think it will be more informative. So the modulus graph, when the function is positive, it's going to be exactly the same, like so. And this crosses the x-axis when this function is equal to 0. E to the x can't equal 0, so x is equal to 5 over 2 is where that is 0. And then the bits below the axis get rebounded up and reflected. So it's just going to be a perfect reflection like so. It was really quite hard for me to draw on the graph, but I think that's pretty good. Yeah, I'll take that. Okay, will I? I'm a bit of a perfectionist, so I'm going to try it again. Down, and then it's going to go like so. I think that's better. Yeah, we'll take that. Okay, so that's the new A coordinate there, and it does ask where it crosses the axes. Yeah, okay. So we need to find what this value is here, and then that will be the reflection of that one. So that is where x equals 0. So let's sub x equals 0 into the original function. So f of 0 is going to give us minus 5 in the brackets, and then e to the 0. So that is just minus 5. So therefore, over here, this is going to be plus 5. So we'll call this one 0, 5, where it cuts there. And like I say, it does say the coordinates, so rather than just labeling the axes, I'll actually write the coordinates. So that was 5 over 2, 0. And that is job done. Okay, implicit differentiation. The curve satisfies this equation. The point P with coordinates 2e to the minus 1, comma 2 lies on C. The tangent to C at P cuts the x-axis at the point A and cuts the y-axis at the point B. Given that O is the origin, find the exact area of the triangle OAB. Right, so first thing we need to do is differentiate. And over here we have a product. So we're going to write u is equal to x and v is equal to e to the 5 minus 2x. So du by dx is equal to 1, and then dv by dx, well, this is actually a function of y. So we have to differentiate it implicitly if we want to work it out with respect to x. So to do so, we just differentiate it with respect to y, and then we times it by dy by dx. So differentiate it with respect to y. The derivative of the input here is just minus 2. So that's what gets multiplied through, and then the power stays exactly the same. And then we have to times it by dy by dx because we are differentiating with respect to x as opposed to respect to y. So that's the foundation of implicit differentiation. Okay, so now we can write this term derivative as this times by this, and then this times by this. So this is going to give me, first off, minus 2x e to the 5 minus 2y dy by dx plus e to the 5 minus 2y. And then we've also got this y here, which when we differentiate that gives me just minus dy by dx. And then 0, well, that will just differentiate to 0. Okay, so now let's collect up the dy by dx terms. We have, how many of them do we have? Well, we have minus 2x e to the 5 minus 2y. That's this term here. And then this term here is just minus, there'll be minus one of them. And that will equal, move this term to the other side, so it'll be minus e to the 5 minus 2y. Okay, now we can divide through to get dy by dx on its own, and we'll get minus e to the 5 minus 2y all over minus 2x e to the 5 minus 2y minus 1. Now, every term there is negative, so we can times through by minus 1 and just turn all the terms here positive, and it's just going to be a little bit neater, like so. Okay. Now, we are looking at the point P with coordinates that, as given here, lies on C. And we want to work out the tangent to P. So we need to work out the gradient at P, so we need to sub P into the gradient function. So dy by dx at the point P. So let's just, on the side here, work out what e to the 5 minus 2 sub in y is 2. What is that going to give us? Well, that is just e to the 5 minus 4, which is e to the 1, which is just e. Okay, so now we can substitute in. So on the top, it will just be e, because like we said, when we sub in the y value into that, we just get e. We've got 2 here, and we're going to times that by the x, which is 2e to the minus 1. And then this e5 to the minus 2y, again, we said when we sub in y, that gives us e, and then plus 1. So because this e to the minus 1 times e is just 1, we're going to end up with 2 times 2 is 4, plus 1 is 5. Okay, so that is the gradient at the point P. So now we can work out the tangent because we have the point P and now we have the gradient at P. So the tangent will be y minus y1 is equal to mx minus x1, a straight line, which is y minus the y coordinate, which was 2. M was the gradient, and that is x minus the x coordinate, which was 2e to the minus 1. Okay, perfect. We could simplify that, but I don't think there's much need at the moment. Let's just leave it as it is. And then what we can do is we can start working out some of these particular points. So it cuts the x-axis at A. Okay, so what we do is we say at A, y equals 0. So it cuts the x-axis. So sub y equals 0 into here, and that gives us minus 2 is equal to e over 5 x minus 2e to the minus 1. Okay, let's solve for x. So times both sides by 5, and then times e into this bracket. So taking that 5 and timesing it to that side, we're taking this e and timesing it into the bracket. We get ex, and we get minus 2e to the minus 1 times e. And what's e to the minus 1 times e? It's just 1. So we're left with that. Let's add the 2 to both sides, and that gives us minus 8 is equal to e x. So x is equal to minus 8 over e. Okay, great. So now let's use this tangent to work out b, because it said that at b is where it cuts the y-axis. Okay. So at b, we have that x equals 0. So sub that into the tangent formula, gives us y minus 2 is equal to e over 5. X is 0, so that's just minus 2e to the minus 1. Okay, let's do exactly the same thing. Let's times the 5 to this side to get 5y minus 10. And then let's times the e inside the bracket to get minus 2 e to the minus 1 e. And as we said before, e to the minus 1 times e is just 1, so we can get rid. So this gives us 5y is equal to, add the 10 over, it gives us 8. So y is equal to 8 over 5. Okay, so now we need to work out the triangle. And if we just draw this on a coordinate axis, a little sketch, we have that A has an x coordinate of minus 8 over e, y, or point B is over here with a y coordinate of 8 over 5. So the triangle that connects AOB looks like this. So the area of that triangle is 1/2 and times the base. So that distance there is, as distance always is positive. So that distance is 8 over e. And the distance, or the height, is 8 over 5. Okay, so this gives us, on top, 8 times 8 is 64. On the bottom, we get 2 times 5 is 10, and then an e as well. And this can be simplified down to 32 over 5e. Perfect. Okay, Newton-Raphson. So it says, show that the above equation has a root alpha which lies between 0 and 1. Okay, so what we do is we say that f of x is equal to the function we're trying to solve, like so. And then, if there is a root, then when we sub in each of the values either side of the interval, then what we should get is a change of sign. So this gives us minus 4 when we sub in 0, and then when we sub in 1, we get 1 cubed plus 10 times 1 minus 4, which is equal to 11 minus 4, which is 7. Okay, and then we have to say the famous and important words, and that is that since there is a change of sign, and f of x is continuous on the interval 0, 1, that means that there is at least one root. Perfect. On the interval. Lovely. Okay, so now it says use the Newton-Raphson method twice, starting with x equals 0.5. Okay, perfect. So what we'll need to do is we'll need to work out the derivative function to use the Newton-Raphson. So let's differentiate this to get 3x squared plus 10. Now the Newton-Raphson formula, which is in your formula booklet, looks like this. It is f of xn over f of xn, f dash of xn. Okay, so let's just use this formula here. And what we're going to do is just expand out the function when we sub in xn. So this is the function. So we're going to replace the x's with xn's in this function like this. Like so. And then over the derivative function, which is this one, so that's just 3xn squared plus 10. Okay, great. So now what we're going to do is we're just going to start with x1 is equal to 0.5, as that's what we're told to do. So the next one, x2, will be subbing in 0.5 like this. In fact, I don't think we need to actually show that we're subbing it in. It's pretty obvious. So what we need to do is just go to our calculator, and we need to do 0.5 equals, and now that becomes the answer button. So then we can press answer, and then minus, in brackets, answer cubed, plus 10 lots of answer, minus 4, over 3 lots of answer squared, plus 10. Press equals, and that will be our x2, and it says to 4 decimal places, so that's 0.3953. And then x3 is just simply the next one along, and if we just press equals again, then it will use the answer right there, the 0.3953, in the formula that we want, and we get 0.3939, and that will be our final answer. Perfect. Okay, Trapezium Rule. It says use the Trapezium Rule with 6 equally spaced strips to find an estimate correct to 3 decimal places for this. Okay, so the first thing we need to do is work out the height of each strip. So the height is going to be the gap between the limits, so 1.2 and 0 obviously has a gap of 1.2, and then we divide it by the number of strips. So this is going to give us 0.2. Okay, so we're going to then need to create a table like so, which has x values starting at 0 and then going up in 0.2, like so. And we should get 7 values because it's 6 strips, so we need 7 values to do that. And this is 1, 2, 3, 4, 5, 6, 7. Perfect. Okay, so we need to do correct to 3 decimal places, and we're going to use our table function to do this. So table function. The function we are looking at is sine of, let's just put that in brackets because we're going to square it, sine of x, there we go, and then that needs to be all squared, so let's just close the brackets and then square it there. Perfect. So sine of x squared, and this will be in radian mode by default, and then let's get, we don't need a second function, and we need to start at 0, we need to end at 1.2, and the steps we're going up in is 0.2. Okay, great. So there we have our numbers. So we're going to put those into here. So we've got 0, we've got 0.039. Again, I'm just doing 3 decimal places, which gives us then 0.151, oh no, 152. And the next one is 0.319. And then we have 0.515, and then we have 0.708, and then finally we have 0.869. Okay, perfect. So there's our table. Now the area, so let's just write this as the integral. So that is going to be approximately equal to height over 2, the 2 endpoints plus 2 times the rest. So the height of each trapezium was 0.2, so divide that by 2. The 2 endpoints are this one and this one. Okay, so that's 0 plus 0.869, and then 2 times the rest, well, it's obviously all the other ones there, so 0.039 plus 0.152 plus 0.319 plus 0.515. Oh, I'm going to run out of space. Can I squeeze it in? 0.708. Close bracket. Okay, great. Oh, close another bracket. There we go. Lovely. Okay, I won't bore you with this. I'll just tell you what this comes out as. Okay, so this comes out at 0.4335. So to three significant figures is 0.434. Okay, I think though, if you did a slightly more degree of accuracy for these numbers, you would get 0.433, which is fine. So either that's the answer or 0.433. I think that's fine either way. Okay. And now it says, use the answer to part A to find an estimate for the integral of cos 2x. So what we need to do is we need to convert this into some form of the one that we know the answer to. Now cos 2x, as we know from our double angle formulas, the integral of cos 2x will equal the integral of cos 2x is 1 minus 2 sine squared x dx. Let's write that in there. Okay. Okay. Great. And the limits I don't think have changed. Always good to check though. No, the limits have stayed exactly the same. Okay, great. So this was 1.2 to 0 and this is still 1.2 to 0. Okay, so we can write this as the integral of 1 between 0 and 1.2 dx and then minus 2 lots of the integral between 0 and 1.2 of sine squared dx, sine squared x dx. Okay, so we can split up integrals like that and we can take out factors as well. Perfect. Okay, so this part we could just do that integral because 1 integrates to x like so, and then we can sub in those limits. Now this is minus 2 lots of, that is I, that is literally part A, which we have an expression for. Okay. So subbing this in, this is just going to give us 1.2, and then when we sub in 0, it's just going to give us 0. And then we're minusing 2 lots of I, which we said was 0.434. Okay, great. So just do that on our calculator. And we're going to get 1.2, whoops, we're going to get 1.2 minus 2 times 0.434, and that's going to come out as 0.332. Okay, great. And now let's look at part C. Okay, so once again, we're going to take this and we're just going to have to use some trig identities here to try and get it to something very similar to what we've had before. Or in this case, it says the part B, so what we've had here. Okay, so that's cos to the 4 sine to the 4. So we can say C, we're looking for the integral, same limits again, of cos to the 4x minus sine to the 4x. And initially, the first thing I'm thinking here is difference of 2 squares. Because both of these are squares, because they are even powers, which means they're squares. So we can use the difference of 2 squares formula, which is that we have a minus b, a plus b. So taking the square root of each of them will give us cos squared x and sine squared x. So we have cos squared x minus sine squared x, open brackets, cos squared x plus sine squared x. Okay, that's great because we know that cos squared x plus sine squared x is 1. So that can cancel out and leave us just with cos squared x minus sine squared x. And then if you're hot on your trig identities, you will know that this is cos 2x. So this is just equal to cos 2x dx. And this is exactly what we've worked out in part B. We literally worked out the integral of cos 2x. So this is going to be the exact same answer as part B. How sneaky. Love that. Partial fractions. Okay. With a differential equation. Classic question this. Okay, let's do it. So 1 over 4 minus x and then 2 minus x. We're saying that is equivalent to a over 4 minus x plus b over 2 minus x, like so. Okay, why does it keep disappearing? Okay. And then what we do is we multiply through by the denominator. So that gives me 1 on this side. And timesing through by the 4 minus x will cancel out that denominator. We'll still have a, and we'll have to times through by this as well, so it'll be 2 minus x. And then timesing both of these by this, the 2 minus x will cancel, and then we'll have a 4 minus x multiplied through as well. And then we think what makes this bracket 0, that will be x equals 2. So we let x equals 2. It won't affect the left hand side because that's just 1. When x is 2, this bracket will be 0. But over here we'll get 2 inside that bracket, so just 2b. And that means that b is equal to a half. And then by the same process we're going to let x equal 4 because that's going to cancel out this bracket. There's going to be a 1 on the left, sub 4 in here, we're going to get a minus 2, so that's minus 2a. So a is equal to minus 1/2. Perfect. It does say express it in partial fractions, so I'm going to go up to the top here, and I'm just going to put these numbers in for a, put the number in for b as well, like so. So that will be my final answer. You could bring the 2 down to the bottom if you wanted to. Both will be absolutely fine. Only 2 marks. Whew, seems a bit harsh, but hey. The mass x in grams, always important to label units, of a substance at t seconds after a chemical reaction starts is modelled by this differential equation. There's the initial conditions, and it says solve the differential equation to okay, so let's just solve that differential equation, and we're going to do that by separating the variables. So I'm going to pick up this dt, times it to this side. I'm going to pick up these 2 brackets, and then I'm going to divide it through, so all the x's on the same side. Okay, so let's do that. Okay, so part B. So that was that dx by dt was equal to k lots of 4 minus x, 2 minus x. And like I say, we're going to times by dt, we're going to divide through by these brackets here. So we're going to get 1 over 4 minus x, 2 minus x, dx is equal to k and dt. So dt comes up, the brackets come down to the other side. And then we integrate both sides in order to solve this. Okay, now what we're going to do is we're going to use these partial fractions. So what I'll do is I'll take a half out in order to just have it slightly more neater. So we're going to say 1/2 of the integral. Now we know this is the same as this, but we've taken the half out. So we're just left with minus 1 over 4 minus x plus 1 over 2 minus x dx. And that's going to equal the integral of k dt. Okay, perfect. Right, let's grab some more space down here, and then let's integrate each of these things. So what is this going to integrate to? Well, let's look at the denominator, and the derivative of the denominator is -1, which is perfect. This means this is going to directly integrate to ln of the denominator. So we'll still get that half, but we'll have ln of the denominator, which is just ln of 4 minus x. Now this one, the denominator is again -1, but on top we've just got 1. So it's going to be the negative of this direct ln integral. So it's going to be minus ln of 2 minus x. Because ideally we'd want a -1 up here, and we could force a -1 up there just by changing this to a minus. So then when we do integrate it, we get ln of 2 minus x, but there's a minus there, so we put the minus here. Okay, close that bracket, and then this is going to integrate to kt, but we're going to need also a constant of integration, so we put plus c there. Okay, what we can do next is we can collect these lns up. So this is going to give us a half of ln, and we're going to have 4 minus x on top and 2 minus x on the bottom, and then kt plus c. Okay, great. Okay, so now will be a good time to sub in those initial conditions and find the constant of integration. So the initial conditions are, yes, 0, 0. That makes it so much easier. And just looking at here, we want x to be the subject. We want x to be the subject, and we also can see that we're going to have these 2 kts. So I think multiplying through by 2 will be useful to get rid of this half and get 2 kts. Anyway, using the initial conditions, we had x equals 0, t equals 0. So subbing this in, we'll get a half ln of, when x is 0, this will be 4 over 2, which is just 2. And that's going to equal, t is 0, so we're just going to get c on this side. Okay, fine, so that is just a half ln 2 is equal to c. Okay, so now let's rewrite this out again, but this time we're going to introduce c. So we're going to write this out, and then we're going to say this is equal to kt plus c, which is a half ln 2. Okay, now we're going to multiply through by that 2 to get rid of these halves. We're going to get 2 kt plus ln 2. Okay, now this ln 2, we're going to minus over here because we want all the lns on one side before we can take e of both sides. Okay, so in doing that, we'll have ln of 4 minus x over 2 minus x minus ln 2 is equal to 2 kt. And then once again, when we minus lns, we can combine them, and then we just divide. So this is going to give us 4 minus x, and then if we're dividing this by 2, it's just going to make the denominator 2 times as big. So that will be 4 minus 2x on the bottom, like that, and that's equal to 2 kt. And now, and only now, we can take e of both sides, which will cancel out the ln on that side, like so, and give us e to the 2 kt. Wow, this is a beast question, this, isn't it? Beast. Okay, so now what we want to do is we want to just make x the subject. So we're going to have to rearrange it using kind of standard skills here. So we're going to multiply this bracket to the other side. So we're going to get 4 minus x is equal to 4 minus 2x, open brackets, e to the 2k. 4 minus 2x, and then times by e to the 2kt. We're then going to multiply this out to get 4e to the 2kt minus 2xe to the 2kt. Okay, and then we're going to move all of the x terms to one side. So let's move this one over here to become positive 2x e to the 2kt minus the x, and then we're going to move the 4 over to this side, so it becomes minus 4. Okay, so just a bit of a swap around, get all the terms with an x on one side. We're then going to factorize out this x, which will allow us to then divide through. These are one of these questions where when you get your final answer, you look up and you just hope and pray that it's the same as the one they're asking for. Okay, so we divide through and we get this. And right, I think that's it. Okay, right, fingers crossed. Is it the same? Yes, that is the same. Yeah, it's just the negative of it. Okay, fine. That's scary. Okay, so let's just times the top and bottom by minus 1, which is just going to flip the signs over. Flip each term over, should I say, which is going to give us like this. Okay, wowza. Okay, that is job done. Okay, and then scrolling up, it just says, given that k is equal to 0.1, find the value of t when x is equal to 1. Okay, lovely. So that's just basically substituting in. Well, I would say that actually, but it's not just that simple, is it? Okay, well, in fact, it's actually going to be easier to use this equation. Because this has t occurring only once. So this is the one that we're going to use. And we're going to say that x is equal to 1. And k was equal to 0.1. So x is equal to 1 and k is equal to 0.1. Okay, so let's just sub in to this purple equation here. So we're going to get 4 minus 1 over 4 minus 2 is equal to e to the 0.2, because, yeah, k is minus k is 0.1, so times that by 2 is 0.2, t. Okay, so this is 3 over 2. And that's equal to that. Then take the natural logarithm of both sides, which gives me this, because it gets rid of the e, and just takes the natural logarithm of the left-hand side. And then times through by 5 to get rid of that 0.2. Okay, so t is equal to 5 ln of 3 over 2, or 1.5, to get an answer of 2.03 to 3 significant figures. Okay, perfect. And we just would have to put the units in there as well, so that should be seconds. Okay, lots of information here to go through, and we've got a cylindrical water tank. Got the diameter is 4 and the height is 2.25, and this is important. It says that water is flowing into the tank at a constant rate of this 0.4 pi, and there's a tap at the bottom where water leaves the tank at a rate of 0.2 pi root h. Okay, so that tells me straight off the bat what dv by dt is, because that's the rate at which the volume is changing. So coming in, so positive is 0.4 pi, and going out, so negative, is 0.2 pi root h. Okay, so I think that will be useful. Now, it's asking us to show that we want to find dH by dt. So dH by dt using the chain rule is the same as dV by dt multiplied. We want to get rid of the dV and we want to have a dH on top. So it'll be like this. Okay, so we have dV by dt, but we don't have dH by dt. So what we can do is we can use the formula for the volume of the water in the tank, and it's a cylinder, so that will be pi r squared times by h. So that is equal to pi, and the r is going to stay the same all the way through, so we can use the fact that the radius is 2, and the height is going to vary, so that is just h. So v is equal to 4 pi h, which allows us to find dv by dh, so that will just be 4 pi, differentiating with respect to h. Okay, great. So now I think we are good to find dH by dt, because it's dV by dt, which is this, which is 0.4 pi minus 0.2 pi root h. And then if I just get rid of this, because all we need now is just this part here. Okay, yeah, there we go. So we just need this part here. And in fact, what we need of it is we actually need the reciprocal of it, because we're looking for dH by dV. So we're going to times this through by the reciprocal of this, which is 1 over root 4. Sorry, 1 over 4 pi. Okay, great. So we can say dH by dt is equal to 0.4, and in fact we can do some cancelling here because we've got a pi and a pi in both terms, and then we are dividing by pi, and then we are also dividing by 4, and then we can divide through by 4, which gives us 0.1 and 0.05 root h. And then we can just look over here and we can see that clearly we've got to times through by 20. Times that by 20 gives us 2. Times that by 20 will cancel the times by 0.05. So we get this as required. Okay, parametric equations, we've got the x, we've got the y, we've got a as a non-zero constant. It says given that the curve passes through the point A, which is 4, 8, find the possible values of a. Okay, so because the curve passes through this point, it means there must be a t value which this point represents. And at that particular t value, you sub it in here, you get x is 4. You sub it in here, you get y is 8. So let's go and find that t value. So we know at this particular t value that the x is 4. So we can sub that into the x equation, which gives 1 is equal to at squared, which gives that 1 over a is equal to t squared, like so. Okay, and then I don't think I can take that much further. Let's leave it like that, and let's sub 8 in over here. So we get 8 is equal to a 2t plus 1. Let's multiply out like so. Let's try and make t the subject. So we get 8 minus a over 2a is equal to t. Okay, great. So like I said before, these two t's are the same because they represent the point A. So what we can do is we can equate them. Okay, so in this instance, just sub that t in over here for this t. So we get 1 over a is equal to t squared. We know t is also 8 minus a over 2a, so we do 8 minus a over 2a all squared, like so. Okay, great. So this gives us 1 over a is equal to 8 minus a squared over the bottom squared, which will be 4a squared. And then we can multiply that up. And when I times this by 1 over a, it's going to give me 4a. Okay, great. So now I can expand that out. And we will get 8 minus a times 8 minus a, which will give us 64. It will give us a minus 8a and another minus 8a. And it will give us a minus a times minus a is just a squared. Right, let's bring this to one side. So minus the 4 gives us minus 20a plus 64. Okay, great. This is a quadratic, so I can just solve this on my calculator. And that is going to give me 1 minus 20 and 64. Okay, great. 16 and 4. Probably should have known that. But hey ho. So a is equal to 4, a is equal to 16. Perfect. Okay, the final boss, parametric differentiation and integration. Okay, so let's start off with part A. And it's basically asking us to find the coordinates of p when theta is equal to pi over 3. So we're just going to sub that in to the x and to the y. So we're going to get 8 lots of cos pi over 3 cubed, which you can literally just put into your calculator and it gives you 1. And then y, we're going to do 6 lots of sine pi over 3 squared. And once again, just into your calculator gives you 4.5. So we can say that p is at 1, 4.5 for 2 nice easy marks. Okay, now part B is asking us to work out the normal to the parametric curve. So in order for us to do that, we're going to need the derivative. So dy by dx is the same as dy by d theta over dx by d theta, which means you basically differentiate the y and then you differentiate the x and you put one over the other. So differentiating the y, okay, we're going to need to use the chain rule here. 2 comes down and times by the 6 to get 12. We keep the function inside the same, but we drop the power down by 1, so 2 goes down to 1. And then we times by the derivative of the bracket, and that will be cos theta. Let's do the same here. The 3 comes down, times by the 8. We keep what's inside the same, but we drop the power down by 1 to make 2. And then we times by the derivative of the bracket, which is minus sine theta. Okay, we can do some cancelling here because we have a sine and a sine. We have a cos, which can cancel with the cos squared to leave cos on the bottom. We have 12 over 24, which can cancel down to a half. And there's a minus here, so don't forget that. And then cos on the bottom is sec. So we can write it like that if we wanted to. Okay, but now we're looking for the normal gradient, aren't we? So we're going to need to use the negative reciprocal. So the dy by dx of the normal is equal to the negative reciprocal of this. So the negative means you take the negative, and there's a negative there already, so it becomes positive. Reciprocal of a half is 2, and the reciprocal of sec is cos. Okay, so we want this gradient at the point which we're interested in. We want the normal gradient at P, so the perpendicular gradient at P. So that will just be 2 lots of cos of the parameter at p, which is pi over 3. So that just gives us 1. Okay, great. So now what we need to do is a straight line equation with the gradient, which we know is what we want, and also the coordinates of p, which is up here. So we do y minus y1 is equal to the gradient m x minus x1, like so. Okay, and then we can expand this out. That's just going to give us 1x. We're going to get minus 1, and then this 4.5 is going to come over here. So this is going to give us y is equal to x plus 3.5 for our final answer. Okay, great. Okay, so now we are asked to work out the region. Okay, so we need to work out the area of this region. Now what we're going to do is split it into a shape and also a section which is underneath the curve. Okay, so this shape here, let's call that region 1, that is a trapezium. And we know that the x-coordinate at p is 1, so this is 1 here. So that means that the gap between the two parallel sides is 1, because it goes from 0 to 1. The two parallel sides are this height here, this distance here, which is going to be the y-intercept of the normal, which we know is 3.5. And this height here is going to be the y-coordinate of p, which we know is 4.5. So we can say that area 1 is equal to the formula for a trapezium, which is half of the two parallel sides added together times by the gap between them, which is 1. And this just gives us, add that together, gives us 8, halved it is 4, so 4. Okay, brilliant. Now, region 2, slightly trickier. So for region 2, we need to work out the limits, because we're going to do this by integration. So the lower limit is parametrically is pi over 3, because we know that the parametric value for p is pi over 3. So what about over here? Well, we know at that point the y is equal to 0. So we set y is equal to 0, and we know that y is also equal to this 6 sine squared theta. So that means that 0 is equal to sine theta, which means that theta is equal to 0 or pi, but it can't be equal to pi because the range is just between 0 and pi over 2. So the only place in the range where sine theta is 0 is when theta is 0. So we know that is going to be the upper limit, which is very crucial. It's not the lower limit, it is the upper limit when theta is equal to 0, and the lower limit is when theta is equal to pi over 3. Okay, so we can start our integral off like that, with the upper limit of 0 and the lower limit of pi over 3. And this is hopefully going to give us region 2. Okay, now what is the formula for parametric integration? It is y dx by d theta, like so. Okay, so the y is the 6 sine squared theta, and then we're going to times that by dx by d theta. So it's the derivative of this, which we have actually worked out, but I've removed it from the screen. What we did is we did 3 times 8, which was 24. We kept the cos the same, but we dropped the power down by 1, and then we multiplied by the derivative of the bracket, which is minus sine theta, and then that is d theta. Okay, so there it is. That's what we need to simplify, and we need to make it look like this, because we've already got the plus 4 from from region 1, so we just need it to be the same as this, hopefully. Okay, so the first thing we could do is a very sneaky trick, and that is we can swap the limits over, and in doing so we have to multiply the integral by -1. So multiplying the integral by -1 in fact swaps the limits over, and I need to do that because the limits are actually this way round, and that's just going to get rid of this minus sign here. We're going to have 6 times 24, which is 144, and that's a constant, so we can keep that outside of the bracket. So now we're going to have sine cubed theta, because we've got sine squared and a sine, and that's times by cos squared theta. Okay, great. And again, the minus was taken care of because we swapped the limits around. Okay, now we want it to look like this. I can see both of these two terms have a sign in them. So what we can do is we can take a sine theta out, which would leave us with sine squared theta cos squared theta. And after taking that sign out, I've noticed that the other factors of these two expressions are all in terms of cos. So let's convert this sine squared into a cos squared by doing sine squared is equal to 1 minus cos squared. So we get 1 minus cos squared, and then that is times by cos squared. Okay, so swapping that sine squared there for a 1 minus cos squared. Okay, and then just don't forget d theta there, and then let's come down here and grab some more space. Okay, so this is now still region 2, and this is equal to pi 144 integral pi over 3 of 0, and then we can multiply this out now. So we get sine times 1 times cos squared. It's just going to be sine theta cos squared theta, and then we're going to get sine times minus cos squared times cos squared is going to be minus sine theta cos to the power 4 theta d theta. Perfect. Okay, so now what we can do is we can just say that the total area, so the total area of region R is going to be 1 plus 2. We said 1 was 4, and then 2 is this integral, and I always forget to put the constant outside the integral. So plus 144 integral pi over 3, 0, sine theta cos squared theta minus sine theta cos to the 4 theta d theta. Okay, brilliant. And that is exactly what they have asked for. And now it just says, hence find the region. Okay, and notice they've actually called the region S. Okay, so region is S. Okay, fine. Well, let's do it then. Let's integrate this. So we're still going to have the 4. That doesn't need to be integrated. But yes, these two expressions here do need to be integrated. And then, spoiler alert, they are reverse chain rules. So we're going to say y is equal to cos cubed. And we know it's a reverse chain rule because we've got this function here, cos, which is raised to a power, and then it's multiplied by its derivative, because the derivative of cos is, well, it's minus sine, but for all intents and purposes, it's sine. It's just times through by a constant. So what we do is we just increase the power of this function here, and we set that equal to y, and then we differentiate it to see how close we get. So when we differentiate this, we get 3 lots of cos squared theta times by cos's derivative, which is minus sine theta. Okay, so this is really close to what we are integrating. It's just out by a factor, it's 3 times too big and it's negative. So what we can do is we can times this by -1/3. And that will make this expression here exactly this. And we have to times this by -1/3 as well, so that this expression now differentiates to this. This is what we're trying to integrate, so this will integrate to this, because differentiation and integration are inverse of one another. So this expression here, which is exactly what we're trying to integrate, integrates to this expression on top. So we can just write -1/3 cos cubed theta. And then we can do the same for this one. For this one, we're going to guess that it is cos to the power 5. We're going to differentiate this. The 5 is going to come down. The cos is going to stay the same, but we're going to drop the power down by 1. And we're going to times by the derivative of cos, which is minus sine theta. Now what I want here, actually the minus is already there, so that's quite handy. But this is 5 times too big. So we need to times this by 1/5. Do the same over here. And now this is exactly what we're trying to integrate. And we know because this differentiates to that, it means that this integrates to that. So we can say plus, because this is actually positive, 1/5 cos to the 5 theta, and that is between pi over 3 and 0. Okay, perfect. So S is equal to 4 plus 144. Cos of pi over 3 is a half, so this is -1/3, a half to the power 3, plus 1/5, a half to the power 5. And then when we sub in 0, careful, when we sub in 0, we do actually get values for cos, don't we? So we need to also take away, so this is the upper limit. So the lower limit, when we sub in 0, we're going to get -1/3, and cos of 0 is 1, so just -1/3. And we're going to get +1/5, because again, cos of 0 is 1. Okay, so it's important that you write out your limits in order to get full marks. So that's exactly what I've done here. Okay, so let's just go to the calculator. Okay, great. So I've subbed in for this bracket here, and I've gotten this. So then I'm just going to times that by 144, and then I'm going to add on 4, and we get our final answer. And I really hope you enjoyed this paper, and I hope you enjoyed my solutions to it. And if you did, I would consider signing up to my live revision sessions and watching me do 2 more papers live. And any questions that we don't get to do, I will create video solutions for those people that have signed up. Yeah, give it a go. Supports your learning and supports me and my channel. Win-win. Hope you enjoyed that. Good luck in your exams. Bye for now.